Hello everyone and welcome to this session. We are here to talk about a random field, which is actually an important concept with many applications, specifically in geotechnical engineering. Let's assume that we are dealing with different layers of soil, and simply because these layers of soil are under the ground, we don't know exactly about the exact spatial distribution of soil characteristics. Let's say if you are talking about the permeability of soil or about the elastic modulus of soil, we don't know exactly how it is spatially distributed. A good solution to tackle this issue is that we think of this spatial distribution as a random field. That is, the characteristic is randomly distributed in the space. But in order to generate a realization of such a random field, we need to know how to implement it. And this is the reason why we are here, to make a practical example and then implement it step by step. So without any further explanation, I try to get into the example. Let's assume that we have a profile of soil with a certain height and width, or a certain depth and width. We are going to generate a random field in this region. The first step that we need to accomplish is to discretize the whole region into different grids or mesh. Let's say, for instance, in the x direction, I'm going to make 100 grids, and in the y direction also I'm going to make 100 grids. So the first step is to define the number of grids in each direction. So let's make a section here with the title, define the size of grid. So on the x direction, let's say 100 grids, and in the y direction also 100 grids. The next step is to define something that we call it a correlation length. The correlation length simply shows the similarity of the neighboring points. Let's say, for instance, if I have one point on the inside this region, how similar it is with the neighboring points. Is it totally different? Or there are some sort of similarity with its vicinity? That's what we call it a correlation length. So here we are to define the correlation length and also variance. So let's say the correlation length is, let's say, 10 meter. That's after 10 meter, the characteristic is going to be much different. But when we are within this 10 meter, then somehow the characteristics are similar. And also let's put the variance as 1. Okay, we proceed with right now generating these grids. Let me make another section here. Generate a grid of coordinates. So for that, I use the command mesh grid. On the x direction, we start from 1 to nx, so that is 1 to nx. On the y direction, 1 to ny. And then I store the result in two vectors, x and y. And that's it. Let me save the code and just simply call it random field. So if I run the code, you will see that the x and y are generated. So here is x is simply the repetition of 1, 2, 3 to 100 in columns. And the y is just something similar but repeated in rows. If I want to show you the grids that we generated, I can simply plot in X and Y. So I can show them by some dots. Also, we can specify the color, let's say blue. And then I can simply plot it. Here is the result. You can see that each of the points here represents a grid. So we already made 100 grids in the X and 100 grids in the Y direction. What we're gonna do in the next step is to generate one random value for each of these grids and then plot the contour of those random values. Okay, let's do it. So I'll put the title of the next section as generate a random field. So I call it as a random field. So I use the standard normal distribution that is with the mean of 0 and the standard deviation of 1. So the resulting value is gonna be like a standard normal values, or simply something that we call it a white noise. So we are using this Gaussian distribution in order to make some white noise for our random field. So I just use the rand normal. The size is gonna be nx and ny, and the mean standard deviation is gonna be 0 and 1 as default. I also multiply it by the variance, although the variance here is 1, but I do so. So if I run the code, we're gonna have the random field generated here 100 times 100. I can here show you the random field generated, I mean the contour plot. So the contour plot of this random field we just generated. And here is the result. Just take a look at this random field here. This is actually a random field, but this is a white noise random field. When I say white noise, that is each point, each grid of this random field is totally independent with the neighboring points. There's no relation, there's no correlation between two neighboring points. So this is simply pure random values for each grid with no correlation. And of course, this is not something that we expect, because in the reality, the soil has some random region. I mean, some regions with, neighboring points are somehow similar. It's not like we have one point here which could be totally different with the neighboring points. This is not the actual condition that we have in the soil. Okay, in order to fix this issue, I'm going to apply the correlation function. So I'll just call it correlation function. What is a correlation function? A correlation function is just a function that helps us to incorporate that correlation length into the random field. And there are different types of correlation function available in the literature. You can simply go through the literature and just try to find the one more suitable for your project. But here we are going to use a very simple one, which is the exponential form of x squared plus y squared divided by the correlation length. Okay, then I put here the exponential of negative x minus x1 squared. I think we need to put two of them here, plus y minus y1 S squared divided by the correlation length S squared. Okay, that's gonna be the correlation function. So if I run the code, you will see the correlation function already generated 100 times 100, right? So we have two matrices. We have one Gaussian, white noise random field and the correlation function. Right now we need to convolve these two. We need to do a convolution process. In order to do so, I prefer to bring these two matrices into the frequency domain. That is, I use a Fourier transform in order to transfer them into the Fourier domain, and then in the Fourier domain, this convolution process is gonna be a simple multiplication. So the new random field or the updated random field will be the fast Fourier transform of the previous random field that we had. Just simply multiply by the fast Fourier transform of this correlation function. But then after doing this multiplication, I use the inverse fast Fourier transform in order to bring them back into the original domain. And here I just care about the real value. I'm going to ignore the imaginary value, if any. Okay, then I run the code. So the random field is already updated. So in the next step, then we just need to plot the random field. I'll make another section. Let's say plot the random field. So what I do is I just make one figure. I plot the contour of this random field. I also put a color bar here. Maybe the title of the graph, let me choose it as just simply random field. Also the X label, I simply put it as X, and the Y label, I'll put it as Y. Okay, right now I run the code. So I hope it is running okay. Yes, it is okay. And here is the random field generated. As you can see, it is actually randomly distributed. That is, if I run the code again, I'm going to get a different field, a different random field, because it is simply programmed based on the random number generated, right? But I can see that there are similar regions here. For example, this region and this region, the region here, the one region here, with more or less similar values. Let me copy this random field and open up a PowerPoint here. Let me just, for instance, paste it somewhere here. Right now, let me increase this correlation length. Let me put it 30, for example. So the resulting random field is again a new random field, but those region is getting bigger, is getting larger, simply because the correlation length is larger, because we are saying that, okay, a larger, a bigger vicinity are somehow similar. So let me copy this one and put it here in order to facilitate this comparison. And if I make this correlation length really a small, let's say for instance 1, and then again generate the random field, you will see that it's really close to the Gaussian, the white noise random field. Those vicinity region, those neighboring region, getting really small, similar to independent noise or white noise. So I again copy the figure and put it here for you. Yeah. Another point that I'm going to make here about this random field is that this correlation length can be different in different directions. For instance, in the x direction and the correlation length in the y direction. They could be different. But here we need to incorporate the correlation length in different directions. So let's say this is the correlation length in the x direction, and then the correlation length in the y direction. So let me put them differently. For instance, let me put it 30 here, and right now run the code. So you will see that the resulting random field will be a little longer in the x direction. Is the regions, the similar region, the neighboring region is stretched in the x direction a little. So I can copy it here in the PowerPoint slide so that you can see it more visibly. And if I put this one 10, but the correlation length in the y direction 30, then the resulting random field will be longer, stretched in the y direction. The neighboring regions are longer in the y direction. I can simply put it here to show it to you. So by using this correlation length, we can simply control the shape of the random field somehow in order to make it in line with reality. Okay, I think it's enough for this session. I hope that you enjoyed the points we just talked about it here.